The graph shown is the graph of f prime of x on the closed interval from -4 to +5. The function is differentiable on the interval and f double prime of 4 is equal to 0. We're going to answer the following questions. Find f prime of -2 and f double prime of -2. The second question is, for what x values does f have relative extrema on the interval from 0 to 5? And that's an open interval. Explain your reasoning. The third question asks us to find all intervals on which the graph of f is concave up and explain our reasoning. The fourth question asks us to find the x value of each of the points of inflection of the graph of f, and we need to justify our answer. And the last question says that if g of x is equal to f of x plus cosine squared of x, is g increasing or decreasing at x equals -pi/2? And justify your answer. Let's get started. First, let's find f prime of -2 and f double prime of -2. Well, we have the graph of f prime right here in front of us, so if we read it at -2, which is right here, we have a y value of 1/2, or a function value at 1/2. And now in order to answer the second part of this, f double prime at -2, we're going to look at the slope of our function here, or how our function is moving. And this section is linear, and it has a slope of 1/2. So therefore, f double prime at -2 is also 1/2. And the reasoning provided for this is we know that f prime at -2 is visible in the graph, and we read it, and that f double prime at -2 is equal to that slope of f prime, which is +1/2. Now let's answer this question. For what x values does f have relative extrema on the open interval from 0 to 5? Explain your reasoning. Notice that we have an open interval from 0 to 5, and we're not including our endpoints. Therefore, we're going to ignore this part right here. We don't need it, because at x equals 0, it's not being included. So therefore, the only place where we will have relative extrema on this open interval from 0 to 5 is occurring at x equals 3, because we are decreasing and then increasing. Our derivative is negative and then positive. So that negative to positive signifies a relative minimum at x equals 3. And again, x equals 0 is not considered because our interval is an open interval from 0 to 5, meaning we are not including that endpoint. Next, find all intervals on which the graph of f is concave up. Explain your reasoning. Well, if we look at our graph, we're actually provided with the graph of f prime. And f prime usually tells us where the function is increasing when it's above the x-axis or decreasing when it's below. But it can also explain to us where concavity is going to happen in the second derivative. Because if the first derivative is decreasing, that means the second derivative will be negative, and we'll have sections of its graph below the x-axis. And when f prime is increasing, that's going to tell us that the second derivative's graph will be above the x-axis. So when looking for concave up, where the second derivative is positive, we're looking for a positive slope for the tangent lines in the graph of our first derivative. And that's occurring where these yellow highlights are found. So it's going to be from -3 to -1 in union with 2 to 3, and then in union with 3 to 4. and again, where the graph is increasing. It's important to note that we have this cusp at x equals 3 where the second derivative fails to exist. That's why we needed to split this section into two separate intervals because we have two separate pieces and there's a corner or a cusp at this point. For part D, find the x value of each of the points of inflection of the graph of f and justify your answer. Well, if we look at our graph that we have of f prime, what we're looking for here are our corners or turning points in our derivative function. Because those turning points where f double prime is equal to 0 or is undefined will end up indicating where those points of inflection are. And this is occurring at x equals -3, x equals -1, x equals 2, and x equals 4. Now let's look at part E. If g of x is equal to f of x plus cosine squared of x, is g increasing or decreasing at x equals -pi/2? And justify your answer. Well, from what we've learned about analyzing functions with derivatives, a regular function increases or decreases when its derivative is positive or negative, respectively. So let's first start off by writing g of x in terms of f of x, which is what we have here, and taking its derivative. So if we differentiate g of x, we'll get g prime of x, which will be equal to f prime of x minus the derivative of cosine squared of x, which can be rewritten as cosine of x squared. So in order to find its derivative, we need to use the chain rule and power rule. So we need to take this 2, bring it out in front. So we have 2, and then we have times cosine of x, and then we have to take the derivative of the inside, or the derivative of cosine x, which is negative sine of x. So that's how we get the simplified equation, g prime of x is equal to f prime of x minus 2 sine of x cosine of x. And now from here, we can evaluate it at -pi/2. It's going to be the same as f prime of -pi/2 minus 2 times the sine of -pi/2 times the cosine of -pi/2. And now if we continue to evaluate, especially the end of our function, we will end up getting that g prime of -pi/2 is equal to f prime of -pi/2 minus 2 times the sine of -pi/2, which is -1, times the cosine of -pi/2, which is 0. Well, since we have the 0 here, this last term is going to go away because any number times 0 is 0. So what we have remaining is that g prime of -pi/2 is equal to f prime of -pi/2. Since we know that g prime of -pi/2 is equal to f prime of -pi/2, let's actually read our f prime of x graph. So -pi/2 is about -1.5, or -1 6/10, so it's right about here. And if we go straight up, we end up at this point. And if we head to the right here, we kind of see that it's a little bit below +1, or it's about at 3/4. So we can see that this value is positive. Mainly, that's the important part. Therefore, g prime of -pi/2 is also positive, making the function g increase at x equals -pi/2.